Good afternoon. I am Fernanditze Gonzalez-Moreno. I'm from Secata Altamira of Instituto Politécnico Nacional in Mexico. I'm going to talk about a DFT study of chromium and cobalt dope zinc sulfide for assessing intermediate band states. The increase in global energy demand and the need to reduce greenhouse gas emissions have driven the search for renewable energy technologies, and currently much of the hydrogen is produced from fossil fuels such as natural gas and coal. While these methods allow large amounts of hydrogen to be obtained, they also generate significant carbon dioxide emissions, contributing to climate change. Faced with this challenge, green hydrogen emerge obtained through the electrolysis of water using energy from renewable sources such as solar. These processes make it possible to produce a clean fuel without polluting gas emissions during its generation, making it a key alternative to move towards a more sustainable and environmentally friendly energy future. One of the most promising technologies are the photoelectrochemical cells. These devices use directly solar energy to splitting water molecules into hydrogen and oxygen using semiconductor materials as a working electrode. Thanks to their potential to generate clean hydrogen using an abundant resource such as solar energy, these cells represent an innovative and sustainable alternative for the transition to this renewable energy. The mechanisms of operation of this device is once of the light falls on the semiconductor, that is the working electrode in the cells, an electron hole pair is produced. The electron is excited towards the conduction band, while the hole remains in the valence band of the semiconductor. The electron is attracted by a countercharge potential applied to an external circuit that leads the electron towards the counter electrode of the cell, where it produces the hydrogen evolution reaction that consequently produces hydrogen, while the hole in the semiconductor produces oxygen at the same time. The efficiency of the process strongly depends on the semiconductor because works as working electrode is needed a band gap from 2 to 3 electron volts. Minimum a conduction band minimum more negative than hydrogen evolution reaction potential, and the valence band maximum need to be more positive than the oxygen evolution reaction potential. For this reason, intermediate band semiconductors have attract considerable attention due to their potential to enhance solar energy conversion efficiency by enable the absorption of subband gap or interband photons. In intermediate band semiconductors, and interband energy photons are absorbed through transitions for valence band to interband, and for interband to conduction band, which together add up to the current of conventional photons absorb to valence band to conduction band transition. The introduction of an intermediate band extends the optical absorption of the semiconductor from the visible region toward the near infrared, allowing the material to use a larger uh, portion of the solar spectrum. As a result, more photons can be absorbed, leading to the generation of a greater number of electron hole pairs. This additional absorption pathway can also reduce carrier recombination losses by promoting more efficiency charge separation. Consequently, these effects contribute to an improvement in the overall solar energy conversion efficiency, making intermediate band semiconductors promising materials for next generation of photovoltaic devices. Then, group 2,6 semiconductors have gained attention and great relevance in recent decades due to the combination of optical and electronic properties that make them attractive for numerous emerging technological applications, because they allow their properties to be adjusted through alloys and doping. Doping in the most of the cases with transition metals, such as chromium, manganese, cobalt, and nickel. Um, this makes them important candidates for uh, applications like solar cells, photocatalysis for hydrogen production, photoelectrochemical cells for water splitting, etc. There is a great interest in abundant and less toxic materials. In this context, compounds such as zinc sulfide stand out for their low toxicity, low cost, high abundance of zinc and sulfur, because they are easier to synthesize, among others. This is why doping zinc sulfide with transition metals have received a lot of attention due to possible tuning of optical, magnetic, electrical properties uh, for application in spintronic and photocatalysis applications, among others. In addition, by doping a semiconductor with a transition metal, introduces an additional energy levels, forming an intermediate band, and this makes the material better used for visible and infrared light absorption, generating more electrons and holes, decreasing recombination, and as a consequence, increasing solar energy conversion efficiency. Then, density functional theory, best known as DFT, is a theoretical method used to study materials at the atomic and electronic level. Instead of doping the behavior of each electron separately, a DFT focuses on something simpler and very powerful. Um, el, um, okay. DFT use um, electron density, that is how electrons are distributed in space within a material. DFT is an indispensable computational tool to study the electronic behavior of in this case, zinc sulfide doped with transition metals by means of the first principles calculation. It's possible to predict the band structure, density of states, charge distributions, allowing us to understand how doping modifies the electronic properties of the material. Uh, and the results obtained by DFT complement and explain the experiment observations or experimentally obtained results, providing a comprehensive view of the mechanisms responsible for the performance of the semiconductor in photoelectrochemical applications. In this application, in a previous work, Espinosa-Faller and collaborators experimentally studied the nanosegregation of chromium and the formation of an intermediate band in uh, highly chromium-doped zinc sulfide films, where uh, they show how the formation of nanosegregated regions affects the generation and stability of an intermediate band in a 2,6 semiconductor. Two important implications for the production of photocatalytic hydrogen were studied. First, that the nanosegregation of the dopant can modify the intermediate state density and the relationship between the absorption of the photon in the subintermediate band within the band gap and the recombination and the structural stability of the system, especially in the region and presence of the electrolyte, this being a critical parameter to guarantee the generation of hydrogen. That's why in this work, a theoretical study of the electronic structure of chromium and cobalt-doped zinc sulfide was conducted using first principles calculations. Using the quantum Espresso program in the supercomputer of the National Supercomputing Laboratory of the Southeast of Mexico, the determination of the electronic properties such as band structure, density of states, and band gap of pristine zinc sulfide was driven following the next procedure. But first is um, important to say that a sphalerite cubic sphalerite sphalerite-like cubic cell composed of 8 atoms was used for pristine zinc sulfide calculations. First, the convergence study was performed, adjusting the Ecot energy, the K points, and the atomic position of the dopants. Then the system was relaxed with the BC relax calculation to obtain the atomic positions. Then, with the self-consistent field calculation, the structure of the material was optimized, and the value of the band gap of the system under study was obtained. Then the graphic of band structure was obtained with using the bands.x calculation. Then the electronic state was generated by using the non-self-consistent field calculation, and finally the density of state graph were obtained through the DOS.x model. And to improve the description of the localized electronic states, uh, a Hilbert correction was used. Uh, this approach reduced the effects of overlapping between neighboring atomic orbitals and provide a more accurate description of the localized states of zinc and sulfur. Also, using JFEFF software, the local electronic properties of chromium and co-doped zinc sulfide were calculated using an sphere of approximately uh, a, hu- uh, 1,000 of atoms containing a simple substitution impurity. This approximation represents the limit of low concentration and allows the study of the local density of states of the dopant without significant interaction between impurities. Uh, the Due to doping with transition metals with partially occupied electrons in 3D orbitals, the calculations were driven under a spin-polarized approach, evaluating the local state density for both spin-up and spin-down states, allowing to analyze the splitting by directions, the exchange of the electronic states associated with dopants, and their possible contribution to the magnetic properties of the system, as well as the possibility of finding intermediate bands in the system. As a result, first are we have the electronic properties of zinc sulfide by in quantum espresso. The results obtained are shown in figure 8, 8A, shows the electronic band structure where the valence band and the conduction band are distinguished. Also, it's observed that the material presents a direct band gap at the gamma point of the first Brillouin zone, and this is a characteristic associated with this material, experimentally with this material in its spherical phase. And figure 8b shows the density of states of sulfur that shows that the p states of sulfur predominates in the valence band, and the uh, states of zinc predominate at the conduction band. In addition, from the calculation from the band gap calculation for zinc sulfide were obtained 3.56 electron volts, like the experimentally, and was obtained also a level Fermi value of 4.97 electron volts, but for convention, value of 0 electron volts of Fermi level is used, and therefore the energy position that are discussed here correspond to values relative to the Fermi level. Figure 9 shows the density of state graphics obtained by JFEFF for chromium-doped zinc sulfide. It's possible to observe the influence of chromium doping on the electronic structure of zinc sulfide, leading to the formation of intermediate bands. Here, this within the zinc sulfide band gap. Likewise, the different contribution associated with the spin polarization, spin up and spin down, can be distinguished. The density of states graphics show the appearance of states located within the band gap for, in this case, for spin up, are below the Fermi level, while for spin down, appear close to the edge of the conduction band or even already within it, which corresponds to those reported in literature experimentally. In addition, the intensity of these contributions is considerably higher than that, than that corresponding to the zinc and sulfur stage, that suggests that these electrons levels are mainly associated with the orbitals, with the 3D orbitals of the cranium, and have a highly localized character. Finally, the cobalt dope zinc sulfide by JFEFF 2 is shown that also significantly modifies the electronic structure of the material, generating cobalt associated states within the band gap region, similar that were observed for cranium. The spin down states are located at energies closer to the upper edge of the valence band, and on the other hand, the states of the spin up appear displacing toward higher energies and are find were find two well-defined contributions, and these are attributable to the 3D orbitals of cobalt, and it's observed as 3 contributions, but it's a lower intensity as compared with the other, and is located near the edge of the conduction band. The high intensity of these peaks compared to the contributions of the zinc and sulfur suggests a predominantly localized character of the dopant-induced electronic states. As conclusions, theoretical calculations shows that zinc sulfide has a direct band gap of 3.56 electron volts at the gamma point of the first Brillouin zone. Likewise, the analysis of the density of states allowed to identify the main orbital contributions of zinc and sulfur in the valence and conduction bands. On the other hand, the calculations carried out using JFEFF show that doping with chromium and cobalt significantly modifies the electronic structure of zinc sulfide by introducing electronic states located with the band gap. In both systems, differences are observed, reflecting the effect of spin polarization on the energy distributions of the dopants' 3D orbitals. The presence of the intermediate band suggests that both chromium and cobalt dope zinc sulfide are materials with potential for applications as intermediate band semiconductors by favoring the absorption of photons with energy below the band gap. Currently, the study of electronic properties of the chromium and cobalt dope zinc sulfide system is continuing by means of DFT calculations using the quantum Espresso package. These results will complement the analysis obtained by JFEFF by determining the band structure, projected density of states, and other electronic parameters of interest, with the aim of understanding in greater depth the effect of doping on the formation of intermediate bands and evaluating its potential for high efficiency photovoltaic applications. Some acknowledgements for Instituto Politécnico Nacional, Cicata Altamira, GESMAT Group, Universidad Marista, Laboratorio Nacional de Supercómputo del Sureste de México y and Simvestab Unidad Mérida. This is the HESMAT group. Thank you so much for your attention. And if you have any answer or contributions, you can contact me through this email. Thank you so much and have a nice day.